In the last video, we saw the dot product, some algebraic operation that we decided was important because of a geometric reason. In this video, we're going to see a different type of operation on two vectors called the cross product, an operation that only works when both of the vectors are three-dimensional. Similarly, we're going to motivate the cross product by looking at a geometric problem. So what I want you to do is I want you to consider two vectors u and v that have an angle theta between them. Now, assuming that those vectors are non-zero and that they're not parallel to each other, these two vectors are going to define a plane. And so what I've sketched here is a plane that is formed by these two particular vectors. Now, our goal is going to find a vector that is orthogonal to both the u and the v, and indeed the entire plane. We're looking for a normal vector that looks something like this. The idea is that when you have some plane, the way it tilts and is oriented in three dimensions, you can get this information out of the normal vector, and hence we're interested in the normal vector. Now, the problem is there isn't one normal vector. This is a normal vector, but this little short one, which is pointing down underneath the plane, is also a normal vector. And indeed, multiplying by any non-zero scalar is going to give another perfectly reasonable normal for this purpose. So that's fine, but I'm going to choose one in particular. I'm going to choose the so-called unit normal that obeys the right-hand rule. The way the right-hand rule works is this. You take your right hand, because it's called the right-hand rule, and first of all, you point it along the direction of the u vector, the first vector that you're considering. So your fingers point in the direction of the first vector. And then what they do is they curl towards the second vector, to the v vector in this case. So they point along u and they curl to v. And then if you stick your thumb up, your thumb is going to tell you the direction of the normal that we're talking about. So in our specific example, you have your u, you have your v, and it curls up to become this normal, which is upwards in our case. If I only demanded that it was a unit vector, there was the two, one pointing up, one pointing down. When you say it's the one vector prescribed by the right-hand rule, it tells you there's only one unique vector that obeys these properties. So that was one geometric problem, but I'm going to tell you about a different one. If I take those two vectors, remember before we'd had a whole plane that was spanned, but I want to restrict myself to the parallelogram that is formed by these two different vectors. It's got the vectors u and v on the one side, and indeed u and v on the other sides as well when you translate them around. So then the question is, what is the area of this parallelogram? Well, the formula for the area of a parallelogram is base times height. Indeed, to see this, you can sort of see that it looks like a parallelogram, but if I take this triangle on the one side, I can sort of put it on the other side, and that would form a rectangle, and rectangle is base times height. So nevertheless, the area of a parallelogram is base times height. Well, what's the height of this thing? I have this value theta, so I know what the height is going to be the length of v sine theta with a little bit of trigonometry on that triangle. All right, so then what is the area of the parallelogram? It's the base times height, so the length of u is the base, then multiplied by this height, so the length of u, the length of v sine theta. Okay, so I'm going to put these two different problems together of finding a normal vector to a plane as well as the area of a parallelogram, and thus I'm going to define my geometric cross product to be that the cross product of u and v is the vector that is in the direction of the unit normal, the n vector, but whose length, the scalar multiple, is the area of the parallelogram. Namely, it's the area of the parallelogram multiplied by that unit normal obeying the right-hand rule. So this is very convenient. This cross product we defined this way solves both of these different problems. But how do you compute it? Now, I'm going to put up on the screen the geometric cross product, and it gives an answer for some easy to compute thing that just spits out the numbers if you know what the u and what the v are. What I haven't justified, and I'm not going to do in this particular video, is the connection. Why is the geometric and the algebraic versions of this cross product really the same? They are connected, and you can show this. But nevertheless, for the purposes of this video, if you want to compute that cross product that we've seen before, well, just plug it into that formula. It looks a little bit messy. And then the final thing I'll note is that if you've seen linear algebra before, if you've seen the idea of a determinant, this messy formula that I don't really like, well, you can clean it up a little bit with a determinant. The determinant form of the cross product is that the cross product of u and v is just going to be, well, in the top row of your matrix, you write ijk, then u1, u2, u3 in the next row, and v1, v2, v3 in the final row, and then you take the determinant of that. If you don't know what a determinant is, that is fine. You can either go and look it up for your edification, or you can just always use the top box, the version that just tells you have to memorize all that annoying stuff. The determinant just gives a slightly easier way to memorize it. Nevertheless, we have an algebraic computation we can do that corresponds to that geometric idea that we introduced at the beginning.